Welcome to this 5-minute short on using ADRIAN for our pressure drops around the relief device, our inlet pressure loss and our back pressure on the relief valve. And this builds on the examples we've been doing around Capri and doing that relief device sizing. So what we've got here, I've just used the system from the 6-second guide, and then we'll amend this for the example that we're using. So we've got an example of using toluene, we've got a relief rate, and we've sized the valve so we now want to understand this pipe work. So the first thing we want to do is look at this vessel. So you can rename the vessel if you want to up here, but I'm quite happy with vessel 1. In fact, no, we could do, why not? Let's call it D303 to keep it consistent. We know it's called, let's put that in there. We've got the contraction type, so is it abrupt or rounded? So this is the contraction from the vessel into the pipework. We normally assume that's abrupt. It's a higher K value, higher pressure loss. If there's a reason to think it's rounded, you can obviously choose rounded, but normally we default to the most pessimistic view when we're doing pressure release, so the higher pressure loss. We now need an inlet flow. So if I go to my sheet and I look at my API sizing, we've got a couple of rated capacity, or a couple of capacities here. One is the rated capacity and one is the actual capacity. Now, depending on which standards you follow, you might want to do your pressure, certainly your inlet pressure loss, on different flows. So API 520 is all about rated capacity. European standards, much more on the angle of actual valve capacities, certainly for inlet pressure loss. So for this example, I'm going to use the actual valve capacity. So we've got 3169. Let's call it that. So 3169. Now we're in kilograms an hour. The program is defaulting at the minute to kilograms a second. So I can put kilograms an hour. I can tab off and it will automatically convert it. Now the pressure, we can put this in there. We know what it is. It's 6.6 bar gauge. That's our relieving pressure. And we know it's about 200 degrees C. Oh, not 2000, 200 degrees C. So where did we get that 200 degrees C from? Again, that came from our physical properties. So 201, keep it a little bit easier. Now, we could copy all these again from that Capri sheet that we've just been flicking to. But what we're going to do, we're going to use that interface into FizzPack. So I'm going to press these three little ellipses, I think they're called. Let's clear methanol out of the way. Let's add toluene to it. Let's take the extended search off so we get just toluene. Double click on that, close. And then you can see here we've got our right temperature and right pressure. But if we weren't happy with this, then we could just type in this. So I can, just for example, I can type 6.6 bar gauge in there. I press calculate, we get the values we need, I press OK. If it had changed that value or that value, then a warning sign would have come up and said, do you want to change that? So again, trying to make it so user aware what's being changed in the software without changing things in the background without people's knowledge. So that's good. We've got our vessel. What I'm going to do now is jump to the valve itself. Now, again, if we go back to our calculation, go back here, we've got a G orifice. So we've got 325 square millimeters. So, and that would be a 1.5 by 3 inch inlet. So, again, look at the pipe diameter. That's actually a 1.5 inch inlet. Just to bring up a little calculator, just to prove that. So, the sizing is correct, but that 562 is too big. I wanted 325, so I could just type 325 in there. Now, the issue I've got is that is an effective area. So what I've put so far is 325 as an effective area, 0.975 as my discharge coefficient, my KD. This is going to be calculating my pressure losses if I just had a valve, ignore the disc for a minute, just a valve on its rated capacity, but that's not what I've got. I've got an orifice area. So what I need to do is increase that orifice area, and this is where derating comes into it. So the wonders of a calculator, these things still exist. We're going to do 325, we're going to divide that by 0.9, and that's going to give me 361. So I'm going to put 361 in there, and that's my actual area, my actual KD, and then I've got what the valve will actually pass, including the actual capacity of the valve. So I'm going to press OK on there. Now the rest of this, we've got some pipe work, we've got some bends. So just to show you how these, we can double click on the bend. We've got a frictional loss here. If I open up the little ellipses, you can see we've got a bend here. So we've got well, let's put that another one in. So we've got our diameter, it understands it's that. Now we have a D of 1, I'm going to put 1 in. So we add that, and you see how these these things pop in. That was actually, let's get rid of that one because it's a 2-inch diameter. We want the 3-inch diameter bend. So we've got a K value in there. We can look at the rest of the pipe work. A good way of doing this actually is to use this little edit fittings here. So we can look at the roughness. And if you want to change the roughness, you can bring the roughness calculator up. And we can have mild steel slightly corroded, because why wouldn't you? You can see we've got our 3-inch pipe work. We're then contracting down into our relief valve, and then we've got our 3-inch pipe work leaving all the way to its exit point. And you can edit it, this in here, so you could bring up the pipe in a diameter calculator, and just for demonstration purposes, I could say it's a 4-inch discharge on that valve, and you'll see that that changes percolator. So ADRIAN does understand where pipe work has to be consistent and where there's, like, if you like, discontinuities, like a relief valve, like an expansion contraction. So it will change what it can do, but with a certain amount of logic and sense. Let's put that back to 3-inch. So that's just another way of viewing and seeing the lengths as you're going through each individual pipe. So we're going to press OK on that. One little word on this is that exit. We haven't looked at exit node yet. Outlet back pressure. So that's 1 atmosphere currently, and that's going to atmosphere. But what this little outlet does is, it built into it is that expansion in the pipe. So obviously in the pipe, the fluid is expanding basically to infinity, into the atmosphere. So in Pell terms, infinity means 10 meters. So built in with that exit model is an expansion from your pipe diameter to 10 meters, just to model that expansion and make sure we understand if there's a choke there or not, because that will affect the back pressures going on. So we've got our model set up. Let's press calculate and let's see what happens. So we've got our, let me just bring that across a little bit. We've got our results here. So the results table, you can see, first of all, it says pipe 1, D303 to exits. Now, in a simple model like that, that doesn't make a huge amount of sense. Well, why are we doing this? But obviously, ADRIAN would do network. So if you had another route in here, and that was a T piece, then this bit here would be pipe 2. So you start getting pipe 1, pipe 2, pipe 3. So it's displaying the summary of that piping system, that particular route. We want to get into the details. So again, let's bring over a little bit more. There we go. So we can see here, as we go down the list, you can see the color changing on the chart. That's so it tells you where things are. Things of interest. This is in blue, nice dark blue. So that's because we've got a choke. So we've got a choke in our valve, and that's what we want. That's what we're designing for, that choke. And I show the velocity as well. So we can see that first. Good check. If you had other chokes, you'd see those in bright blue as well. If they're after the relief valve, that's absolutely fine. If there's any choke beforehand, we'd have a bit of an issue going on. So that's all good. But what we want to do is want to understand our back pressure, and we want to understand our inlet pressure loss. So you'll notice that what ADRIAN does, it displays static pressure and stagnation pressure. Now for your back pressure, that's the flowing pressure at the outlet flange of your valve. So in this case, it'll be this number here, just slightly above 1 bar absolute. So our back pressure is going to be absolutely fine. But that's the number it's going to pick. But for our inlet pressure loss, it needs just the irrecoverable losses due to friction. And to make sure we only pick those up, it's going to look at the stagnation pressure, and it's going to delete one stagnation pressure from the other to get our inlet pressure loss. If we did it from here, you can see the static pressure. That static pressure is slightly lower than the stagnation pressure. And that's all to do with Bernoulli's. So we've borrowed some of the pressure energy to convert it into kinetic energy. So if you read the pressure with a pressure gauge on the side of the pipe, it would be a slightly lower pressure. But obviously we don't want to include that extra 0.1 into our inlet pressure loss, because that's not an irrecoverable loss due to friction. That's just Bernoulli being Bernoulli. So we need to make sure we pick the right pressures up, and that's what ADRIAN does. So if I go to my relief valve, I can click on pressure losses, and then here we've got a little menu that pops up. So our set pressure was 6 bar gauge. Our overpressure is 10%. So my relieving pressure is 6.6 bar gauge, or 7.61 bar absolute. Takes 1 bar absolute a minute. Real quick check in ADRIAN. This number here, and what that number is this number here. So when you first get an ADRIAN calculation for pressure drops, check those two numbers. And if they're close, and in this case I've got 7.61, I'm correct to, depends if you're rounding or up, at least 1, potentially 2 decimal places. I'm happy with that. That's okay. But that's my quick check. If they were very different, there's something wrong in the model. But I'm happy with that. Then I can check. So I've got 1.08% upstream pressure loss. I've got 1.27% back pressure. So that fits with my requirements of pressure relief 3%, 10%. Happy days. This system is okay. And that's how I would check or calculate my pressure loss valve relief system and check they were okay. Thank you.